Ladies and gentlemen, welcome to the ICDTDE2025 conference. My name is Huquit Tran, representing the Faculty of Electronics Technology at the Industrial University of Ho Chi Minh City, Vietnam. Today, I am honored to present our research paper titled Performance Energy Efficiency Trade-Off Analysis of Distributed Multi-RIS Systems Under Co-Channel Interference. This work was conducted in collaboration with my colleagues Dien, Phan, and Hao Li.
Here is the outline of my presentation. I will begin with the motivation for multi-RIS in 6G and the challenges we addressed. Next, I will describe the system model and the proposed schemes. Then we will analyze the mathematical framework and discuss the simulation results, focusing on the trade-off between performance and energy efficiency. Finally, I will conclude the presentation.
Let's start with the motivation. As we move towards 6G, there is an exponential demand for both spectral efficiency and energy efficiency. Reconfigurable intelligent surfaces, or RIS, have emerged as a key enabling technology to program the radio propagation environment. However, in complex urban scenarios with dense obstacles, a single RIS is often insufficient due to blockage. Therefore, deploying distributed multi-RIS systems is essential to ensure reliable coverage and connectivity. However, analyzing such systems comes with significant challenges. First, the channels associated with distributed RIS surfaces are independent and non-identically distributed, which we model using Nakagami M fading. Second, in multi-cell networks, CO channel interference becomes the primary limiting factor. To address these, our paper contributes a comprehensive statistical framework using the method of moments. We specifically aim to quantify the complex trade-off between ergodic capacity and energy efficiency under the impact of interference.
Please take a look at our system model. We consider a downlink network where the source, BS0, communicates with the destination, supported by 5 distributed RIS surfaces. The critical challenge here is the co-channel interference originating from 2 neighboring base stations, BS1 and BS2. The user receives a superposition of the direct signal, the reflected signals via the RIS surfaces, and the interference. To ensure realism, we model all these links as independent but not identically distributed Nakagami M fading channels.
Based on the system model, we formulate the instantaneous signal-to-interference plus noise ratio as shown in equation 1. The numerator represents the desired channel power, which depends on whether we use the ERA or ORA scheme. The denominator is the critical part. It includes not only the background noise, but also the aggregate co-channel interference power originating from the neighboring base stations. This mathematical formulation allows us to strictly evaluate how interference limits the system performance.
We propose 2 transmission strategies. The first is the exhaustive RIS-aided scheme, or ERA. In this mode, all distributed surfaces are activated simultaneously to reflect signals to the user. This approach maximizes the array gain and spatial diversity, ensuring the highest possible signal reliability, though at the cost of higher circuit power consumption.
The second strategy is the opportunistic RISA-aided scheme, or ORA. Here, the system estimates the channel quality and activates only the single best surface that offers the strongest link. By keeping the other surfaces idle, ORA significantly reduces hardware energy consumption, making it a greener alternative for energy-constrained scenarios.
To evaluate the trade-off, we model the total power consumption as the sum of the transmit power and the circuit power. The key difference lies in the circuit component. For ERA, the power consumption scales with the total number of elements across all surfaces. In contrast, ORA only consumes power for the selected surface, resulting in a much lower energy footprint.
Finally, energy efficiency is calculated as the ratio of the system throughput to this total power consumption.
Moving on to the mathematical analysis. Analyzing the performance of distributed multi-RIS systems is mathematically complex. This is because the end-to-end channel involves a sum of products of random variables, and the presence of co-channel interference adds another layer of difficulty. To solve this, we employed the method of moments framework. The process begins by characterizing the raw moments of the independent and non-identically distributed Nagagami M fading channels. Instead of using computationally expensive Monte Carlo simulations for every scenario, we match these moments to approximate the distributions of the desired signal and the aggregate interference power using gamma and log normal distributions. This rigorous approach allows us to derive closed-form expressions for both outage probability and ergodic capacity.
Now, let's analyze the simulation results, starting with outage probability. This graph plots the outage probability against the source transmit power. The red curves represent the ERA scheme, while the blue curves represent the ORA scheme. Clearly, the ERA scheme provides superior reliability, shifting the curve to the left compared to ORA. This confirms the benefit of diversity gain when using all RIS surfaces. However, the most critical observation here is the impact of interference, shown by the dashed lines. Unlike the solid lines, which assume no interference, the dashed lines do not decrease indefinitely as we increase the transmit power. Instead, they flatten out and hit a saturation level. We call this the interference floor. This phenomenon proves that in a multi-cell environment, simply increasing transmit power cannot eliminate outage events.
A similar trend is observed in the ergodic capacity analysis. Here, we compare the capacity in bits per second per hertz against the transmit power. The red line, representing EROA, consistently stays above the blue line, representing OROA, across the entire power range. This quantifies the spectral efficiency gain achieved by coherently combining signals from all 5 distributed RIS surfaces. However, please pay attention to the dashed lines. While the interference-free capacity grows linearly with the logarithmic increase of power, the capacity under interference, shown by the dashed lines, grows much slower and eventually saturates. This result is crucial for 6G network planning. It suggests that without advanced interference management techniques, the capacity scaling promised by multi-RIS deployments will be fundamentally bottlenecked. Next is another perspective, the relationship between the required transmit power and the achievable rate. In this graph, the x-axis represents the target rate we want to achieve, and the y-axis is the power needed to reach that rate. As you can see, the ERA curve, shown in red, is positioned to the right of the ORA curve, shown in blue. This means that for any specific target rate, the ERA scheme requires significantly less transmit power compared to ORA. This effectively confirms that ERA is the more spectrally efficient strategy. It is the ideal choice for applications where maintaining a high data rate is the priority, provided that the power budget allows for it. Finally, we arrive at the most significant finding of our research, the energy efficiency trade-off. This graph plots the energy efficiency, measured in megabits per joule, against the average achievable rate. The behavior here is distinctively bell-shaped. In the low-rate region, on the left side of the graph, the ORA scheme, shown in blue, dramatically outperforms ERA, achieving a much higher peak energy efficiency. Why does this happen? It is because at low rates, the transmit power is small, so the circuit power dominates the total consumption. Since ORA activates only one RIS, it saves a massive amount of hardware energy. Conversely, ERA suffers here due to the high energy cost of keeping all surfaces active. However, as the rate increases, ERA becomes more efficient. This clearly demonstrates the trade-off.
ORA is the green solution for low-rate IoT applications, while ERA is necessary for high-throughput demands.
To conclude, our work goes beyond just mathematical derivation. We have unveiled the critical balance needed for future sustainable networks. While ERA pushes the boundaries of speed and reliability, ORA emerges as the champion for green 6G communications. However, the interference floor remains a fundamental challenge. This finding serves as a vital reminder that to fully unlock the potential of distributed RIS systems, we must look beyond transmit power and focus on advanced interference management.
This brings us to the end of my presentation. It has been a privilege to share our findings with the ICDTDE community today. I truly appreciate your time and attention. If you have any further questions or insights, please do not hesitate to reach out via email. Thank you and goodbye.